Okay, so we're going to look at square roots. And we're just going to do it by example. Okay, square root of 50. Simplified, completely simplified. The perfect square is 25, and so we're going to write this as 5 root 2. Whenever you see a square root in your problems, it should always be completely simplified. It means the perfect squares should be taken out of the radical. Okay, if you see, okay, a radical in the denominator, don't yell it. Completely simplified means no radical in the denominator. Does anybody remember how to do this? Laura? You multiply the top and the bottom by the square root of 3. Yes? Okay. And so the top, you multiply these two things together. And on the bottom, you get root 3 times root 3, which is 3. Okay, so here's a vocab word. This is called rationalizing. Okay, rationalize. That's actually a verb. It means to do something. It actually means to turn, make the denominator a rational number. Like, okay, I don't know what a rational number is. I'll define that next. Rationalize is an action word. That is the direction. Okay? A rational number rational number is, first, it is a real number. Everything you've done so far is probably a real number. It's a number on the number line between negative infinity and positive infinity. Right? All real numbers. It's between negative infinity and positive infinity. But there's a second characteristic to a rational number. Second, it's a ratio of integers. That's what a rational number is. That's why it says ratio first. Ratio number. Ratio of integers could be 3 over 1, 2 over 3, negative 4 over 5, negative 2. All of those things are rational numbers. So I rationalized this because I turned the denominator from a radical into an integer. That's what the directions say. Rationalize the denominator. Means turn it into a rational number. All right. So anybody know why you can multiply by root 3 over 3? Right? It's not a trick. There's a reason you can do it. Because it just means 1. Go grab a piece of candy. We have candy today. We added some goodies from last week. There's some stuff in there. And there's Airheads and Starbursts.
Oh, nice.
Yeah, okay. And we'll, right, for answering some questions. All right, guys, another vocab word. Multiplicative. Identity. Identity is 1. When you multiply by 1, you get the same number, right? You get something that is equal to it. Why can you multiply by root 3 over 3? Guys, this is not an equation. There's no equals. There's properties of equality, and there's properties of identity. multiplicative identity is 1 because A times 1 is still A. That's why you're allowed to multiply by root 3 over 3. It's the multiplicative identity. I like to call root 3 over 3 fancy form of 1 because root 3 divided by root 3 is equal to 1. That is a very useful strategy. Sometimes we make 1 look a lot of different ways depending upon the type of problem we start with. Okay, so I'm going to make this a little trickier. Do not yell this answer out. Completely simplify that radical, right? Which means simplify the square roots if possible and rationalize. Simplify implies that you will also rationalize the denominator. These are skills you have done before, but not necessarily with this vocab. Does anybody have the answer? Yes, Ricky? Yes, root 6 over 6. You can come grab a piece of candy. Okay, how did you get it? What did you do first?
I did square root of 2 over square root of 12.
Okay, so there's two. He did this. He did square root of 2 over square root of 12. What did you do next? Rationalize. This is the long way. He got the answer, but this is the long way. How did you rationalize? Yep. Okay, so that takes me to a root, what, 24? Over 12. Not done yet. 24's got a 4 in it. It's 4 and 6, so that's a 2 root 6 over 12, which takes me to completely simplified. Did anybody do it a shorter way and say maybe 2 steps? What'd you do, Avi?
Well, you made square root of 12, 2 square root 3.
Okay.
Then you rationalize.
Okay, so he saw the 4 times 3 and the 12, right? He saw the perfect square first. Okay, then he decided to rationalize. Go ahead and grab a piece. Okay, so he did root 3 over 3. And so root 2 and 3 is this. And then 2 times 3, right? 2 times, that's a times there. You can dump it out or pop the lid off. Okay, so root 6 over 6. Did somebody do it even, well, same number of steps but different? Okay, Lily?
I don't know if this is right, but I simplified the fraction first. I did 1/6, and then I rationalized.
Yeah, got 2 and 12 reduce. And then, yeah, go grab a piece. This is what I would have done. I would have seen the 2 and 12, and I would have automatically said 1/6.
Yeah.
None of the other methods are wrong, guys, but it's how much writing are you going to do and which numbers are easier to work with. Okay, so root 6 over 6. The second and the third choice are almost the same amount of work because you reduce the numbers before you go, right? But you all get the same answer, completely simplified. That's what we're aiming for. When you learned how to rationalize the first time, you weren't talking about efficiency, you were just talking about doing it. I need you to be efficient. I need you to be in number 2 or number 3. Like, you gotta be here. You can't do here. You're gonna run out of time. You will eventually end up with numbers that are not very feasible to do this first way. So you're gonna need to start looking at reducing and simplifying numbers before you rationalize. Okay, so review first. Okay, solve. for x. Right? Why do we have square roots? X squared equals 27. Always give me completely simplified answers. Notice that as we go through our units or standards, we're kind of in standard 3, which is all about quadratics. An intro to quadratics means my degree, there's a vocab word. Degree is the highest exponent. So in this particular example, the degree is 2. Okay, who has a solution? Gavin?
3 root 3.
Almost. Yeah. Okay, the degree is 2. Degree 2 means there will be 2 solutions. Implies 2 solutions. Okay, you're like, well, why do I have plus or minus? Guys, a negative times a negative is positive, right? You're squaring it. Negative times negative will equal a positive number. And so I have to consider the negative as a possibility because of the squared exponent. That's why you end up with 2 solutions. I can make it simpler and just say x squared equals 25. Yeah, perfect squares are pretty easy. You're like, oh, negative 5 times negative 5 is positive 25. Plus or minus 5. Where's your check? Yeah, equals positive 25. 5 squared. Would I check this? No, because something squared will always be positive. But I have to make sure I know there's a plus or minus answer here. Okay, there's the review. Now we're going to start getting into the new stuff that looks kind of similar to what we've just done here. This begins your 3.1. Okay. Complex. Sometimes these are called imaginary numbers. Okay. Algebraic definition. Solve for x. It's easiest to do this definition by example. What's x? Daniel? Okay, yeah, I like that. Okay, so he says x equals plus or minus square root of negative 1. I mean, yes, I square rooted both sides. I have plus or minus. Give me 1 second. Okay. Got a piece of candy.
Oh, nice.
Yeah. Okay, that's it. Guys, but have you ever done the square root of a negative number? I know you have. You're like, it's not possible. It's not really possible. This is your algebraic definition of a new type of number. Okay? The square root of negative 1 is defined as I. imaginary, which is not real. Okay, everything you've done so far has been a real number. So now we need to figure out, how do I do a solution with the square root of a negative number? Well, we define a new number. This is an algebraic definition. Instead of writing square root of -1, we write I. It's like a substitution. All I is a shorter, simpler way to write square root -1. That's it. Okay, so what would I squared be equal to? Don't yell it. Gabe?
That it has to be -1?
It is. Grab a piece of candy. Okay, so that just means you multiply the same thing twice. Well, what's root -1 times root -1? -1. Guys, this is an algebraic definition. Okay, so I'm going to put ... because I could keep upping the powers of I. So I cubed, Laura?
1.
Not 1. Not -1. Rafi? -I. You can have another piece if you'd like. Okay? What about I to the 4th? Don't yell.
Wait, how did he do that?
Okay, good question. So how about, that's all right. What if I just take the two previous lines, I and I squared? If I multiply I and I squared, I get I cubed. Yes?
Yeah.
Yes? No?
Yeah.
Okay, so if I take I and I squared and I multiply them, I get I cubed. Okay, so take the two things above it. I times -1.
Nice.
It's a bunch of substitutions, right? I'm just going to the previous lines and I'm substituting things that, like, I've built my definition up. I start with this, and then I do I times I. And then I do I times I times I. And I start replacing the things that I can replace. And so what if I do I to the 4th? Not I. Wait. Yeah? 1. Grab a piece. 1. Okay, it builds from the previous definition. Why do we have I? It allows me to solve equations that I didn't think I could solve. Okay, so let's give you maybe one more example. Okay. In simplest form, solve for x, simplified and rationalized if necessary. 2x squared equals -8, and 6x squared equals 2. -2. Different equations. Just two examples. Solve for x. So we started with something you could do, and we seamlessly turned it into something a little bit new, but the algebra still feels the same as what you were doing before. Okay. Answer. Does anyone have an answer for this first one? Gabe?
I think I'm wrong, but I got a 2I.
You are not wrong. You're not all the way right. Lily?
Would it be 4I?
2I is closer. Do you know what you missed?
Did I miss like plus minus?
Yes, the plus minus. Right? The degree is 2. Means I should have 2 answers. Every time you square root, when you are solving, you will get 2 answers. Okay, so yes, I did my PEMDAS. I got -4, and then I square rooted. Okay, so I'm just going to break this down because I know that 4 is the perfect square, and then I've got the -1. And so plus or minus 2I. I'm replacing the things, right? -1 is not really a perfect square, but it is equal to I, and that's what I'm substituting. So x equals plus or minus 2I. You don't need the times between them. It's just plus or minus 2I. Okay, this one's for Candy. Completely simplified. What is the answer to this one? Don't yell it. This one's for Candy. Okay, I'm ready. Hold on. Give him a chance, and then I'll ask you. Hold on. He had his hand up first. We'll give him a chance. All right, Avi.
Plus or minus I over 3 over 3.
Yes. Right. Say it again. Make sure I heard it right.
Plus or minus I square root of 3 over 3.
Yes. Okay. Tell us how you got there.
Well, I first divide by 6.
Okay.
Then I square root it to get plus or minus I square root of 1/3. Then since
Hold on. You're talking too fast. Okay. So we're here, and so he's got. I'm just doing a little bit of rewriting. Okay. So I divided 6, and I reduced, because why not? Then I square rooted, and then I rewrote it, right? I didn't really simplify it. I just rewrote it with the taking out the radical that I could. Root -1 is replaced by I. Okay, and then what? And then the very last thing I do is rationalize it. Means you should simplify, then rationalize. All right. Okay, so geometric definition of I. Okay, so we have standard form, okay, which is, I'm going to use capital letters, A plus BI. A is the real part, okay, this is the real part, this is the imaginary part, where both A and B are real numbers. Okay, why is that the imaginary part? It's got the I with it. Okay, where A and B, look at this notation. It looks like a curved E, means element of the real numbers. It means A and B are real numbers. This is the format that you should be writing your numbers in. So far, you've just seen the examples that have a coefficient in front of your eyes. Right? It's just been eyes. Now we're going to start adding a second part, a real number in front. Okay? Now, this together is called a complex number. Complex or imaginary number. Usually when we get the two pieces together, we call this complex number. Which sometimes people interchange complex and imaginary because complex numbers have an I. Okay? This is the format that you should be writing your answers in. The real number plus the imaginary part. How do you graph an imaginary number? Okay. I'm going to relabel my axes. We have a real axis and an imaginary. You can label your axes anything you want. They don't have to be X and Y. Okay? So my first example is 2 plus 3i. Where would that go on the graph? Well, the real part is 2. So I'm going to put this like in a coordinate pair. 2, 3. This is the real part. This is the imaginary part. Notice how I'm just taking the numbers, the part that we usually put on a coordinate grid. 1, 2, 1, 2, 3. This is the point 2 plus 3i. You get it by taking the numbers 2 and 3. The X is for the real, the A part, and the B is for the imaginary part. -2 minus I. So the number is -2, -1. Notice how the axes are labeled real, which is for the A number, imaginary, which is for the B number. Okay, so this one would go 1, 2. This point right here is -2 minus I. I'm just writing down the coordinates that would, right? That's what matches how you typically plot your points. Okay. New axes. Plot I. Plot I. What's the real part? What's the imaginary part? Zero, 1. 0, 1. Did you know that I can be defined as a 90-degree rotation?
Whoa.
Okay. What, okay, I squared, we kind of already developed this idea that I squared is -1. Put it on the graph. Notice how that position rotates 90 degrees. This is more of a conceptual understanding of what I is. The actual algebraic manipulation and operations is pretty straightforward, but understanding like what I is a little bit trickier. So this is -1. Now I'm going to put equals I squared here because it's going to be useful. Okay. What about, where does I cubed show up on the graph? I is a 90-degree rotation. This is one of those concepts that would show up in what used to be like math league problems or the AMC 10 or 8, 10, or 12 questions where they do more conceptual type problems. Okay, so what point goes here? Negative I. Keep in mind, this is what makes sense with what we just plotted. That's just 0, negative 1. Oh, what was I cubed? Negative I. Okay, rotate again. What goes here? Positive 1. Sometimes this is called an I clock because you're rotating like a clock. I can keep going. Like, what would I to the 5th be? It's another 90-degree rotation. And I to the 6th, rotate again. I to the 7th, rotate again. I to the 8th, rotate. 9, 10, 11, 12. I is a 90-degree rotation. Geometric, right? Graphically, visually, how can I define I? I is a 90-degree rotation, which we just did. Okay? So if I'm going to be powers of I, let's see, powers of I. I to the 5th. Okay. I'm going to break it down. I to the 4th times I to the 1st. What's I to the 4th? 1 times I. Remember that we have to write our answers in standard form. That means you can't have more than a first power of I. It means if you have higher powers, you need to reduce the powers to an equivalent form. Okay, I to the 18th. 4, 4, 4, 4. Because if I look at my clock, I'm going to, all powers of 4 come out to be positive 1. So I start here, first power. That's why I left the powers here. I to the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 1 times I squared. Well, I know that I squared is negative 1. Okay, so I'll be really fancy for a second. All right, guys. What's one of the biggest multiples of 4 you know? 12 is kind of small. Let's go with 100. Is 100 a multiple of 4? Yeah, think bigger, guys. 100. Is 1,000 a multiple of 4? Okay, so what number are we really looking at here? Not 1,000. Not 200. 25. Is 20 a multiple of 4? Oh, you're just looking at 5. Right? I worked my way down. Okay? I to the 1,000. 1,000 is a multiple of 4. It's just 250, 250, 250, 250. Okay. 200. Oh, 200 is a multiple of 4. I'm trying to take out my multiples of 4. I'm just starting with the thousands place. Okay, what else is a multiple of 4? 20. What's left? Just 5. Okay. Gives me 1 times 1 times 1. Oh, okay, I to the 5th. What's my leftover? I, thank you. Okay, I will go I to the fourth times I. Do I need to see all of that? No. You could probably just pick the closest multiple of 4 and replace it with 1. But this gives me just I. But you have to get the powers all the way down to 1. That's it. 1 is the highest power. Almost there, guys. I know. Okay. D. Add. Subtract. I'm going to go multiply. I don't think they need to be separate categories. Okay. 4 times 2 minus 3i minus 2i times 3i minus 1. Okay, PEMDAS. Combine your like terms, right? PEMDAS. Operations. Combine your like terms. Do your operations in order. Just be careful with your negatives. Okay. Okay, so I noticed that my answer is not in standard form, which means you have to reduce the powers of I so that you can put it in standard form. Okay, right here. I know that I squared is really -1. So that's a +6. So really, I have 14 minus 10i. Okay, because see that I squared? When I distributed, I got I squared, but standard form does not allow for powers more than 1, which means I had to replace the I squared. Divide.
Well, from back from the beginning part, when you have minus it should wouldn't it be -6 minus 2i for the second part?
Oh, minus minus is plus. Minus minus. So you want to make this a plus and then a negative? You're distributing the negative.
But
That's the
so
part.
you only end up where you have it there. You only end up with one number, not 2 for the second part.
No, because the first term is I squared. The second term is
that's-
just I.
I didn't see the I.
Good?
Yeah, I didn't.
Okay. All right, so now we're going to look at divide. Let's see. Let's pick a question. Okay. 2 minus I over 3i. What might be the problem with that? Well, first thing, it doesn't look like this. Second thing, that's a radical in hiding. Where is my radical hiding? In the denominator. Divide, simplify, rationalize, right? So divide, this is simplify, and there's the verb, rationalize the denominator. Okay, well the problem is that the I is really a radical in hiding. just like we started with the review, what will we multiply by? How am I going to turn 3i into a rational number? Think about your powers of I. What kind of power is going to get rid of the I? There's two of them. Which power of I gets rid of the I? Squared. If I square I, it turns into -1. But I'm not allowed to square things, guys. Property of equality. The only thing I can do is multiply by 1. I'm going to do this because I want to. Multiply that -3i through the top and the bottom. And let's just see what happens. Minus 6i plus 3i squared, -9i squared. And I chose that -3i on purpose. Okay. Replace the powers of I because I can't have I squared, right? I'm aiming for standard form. -3 +9. I circled the places that I was replacing, right? I squared is -1. And so in the denominator, I ended up with negative times negative, which is positive. I like positive denominators. And reduce. Do you notice how 3, 6, and 9 are all multiples of 3? Okay, so -1 minus 2i over 3. That's not quite standard form, guys. Minus 1/3 minus 2i over 3. It's actually split up as separate fractions as standard form. Right? Because I need to know what the real number is and the imaginary number is. So in case I wanted to graph it or something. Okay. Last one. I know. 4. 2 plus I. Mrs. Teresa. What am I going to multiply by? Right? This property of equality, guys. There are grouping symbols here. It's got to get fancy. It's not too fancy. Just a little bit fancy. But there's a vocab word here. Conjugate pairs. When you multiply conjugate pairs together, the result is a rational number. Oh, okay, that's what I want. When conjugate pairs are multiplied together, the result is rational. Result is rational. Okay, so what are conjugate pairs? Okay, A plus BI. In standard form, obviously. A minus BI. It's kind of like a difference of squares pattern where the inner and the outer disappear. And the last is an I squared, which turns into a rational number, right? Keep in mind, we're still rationalizing that box is still equal to 1. What am I trying to rationalize? The denominator. Okay, so let's distribute our top. 8 minus 2i. Okay, first, outer, inner, last. Oh, yeah. Nice. Okay. Right? I squared is what turns into -1. Yes. Thank you. Okay. Okay, so I've got 4 plus 1. 8 over 5 minus 2i over 5. 4. 4. There you go.